Prim's algorithm. Prim's algorithm is a greedy algorithm for finding minimum spanning tree of a weighted, connected and undirected graph. What is a minimum spanning tree? Minimum spanning tree of a graph G is a subgraph of this graph which is having all the vertices connected together with minimum number of edges and with minimum possible total edge weight. This is what is a minimum spanning tree. So whenever these properties are satisfied, the total number of edges will be v minus 1. Here v is the number of vertices. So whenever you want to connect v vertices with minimum number of edges, the total number of edges will be v minus 1. And if you want to know in detail about minimum spanning trees and spanning trees, please refer to our spanning tree lecture and minimum spanning tree lecture under data structures lecture series. Though we had detailed about all the properties of these, but for now you just need to understand what is a minimum spanning tree. That is good enough for this lecture. So minimum spanning tree is a tree, a subgraph of G such that you are connecting all the vertices with minimum number of edges and lowest possible total edge weight. This is a minimum spanning tree. The next question is, we already told that this is a greedy algorithm. So what is the greedy approach that we are taking in order to form a spanning tree or a minimum spanning tree using Prim's algorithm? The greedy approach is that we'll build the MST, that is minimum spanning tree, by starting at an arbitrary vertex, any vertex, and then iteratively adding the shortest edge that connects vertex in the MST to any vertex outside the MST. So the concept is like this. If you have a graph like this, if you remember our previous Kruskal's algorithm lecture, though we always pick the smallest edge as our first step. That is, whenever you wanted to pick the first edge, you picked whichever is the smallest edge possible. Here we are saying that you can pick any vertex arbitrarily. So this difference is because whenever you are choosing edges, you have to be careful. The MST of the graph, this may not have all the edges. So if you choose the smallest edge, you are safe because you know this edge can be part of MST. But coming to vertices, all the vertices of this graph will anyway be part of the MST. So you are free to choose whichever vertex you want to start from because they all will be anyway part of the MST. This is why in Prim's algorithm, because we go by vertices and not edges, you are free to start from any vertex arbitrarily. So let us say you started with this vertex. Then what you are considering is whichever is the vertex that you have selected, that you are considering as already part of MST. And all the other vertices, they are not part of MST for now, but you have to take them into the MST by adding required edges. So what will you do? You will see which is the edge inside MST and which all are the edges outside MST, and then you will greedily pick the smallest edge possible which can connect a vertex which is inside your MST to a vertex that is standing outside the MST. This is the logic used by Prim's algorithm. So we have to go into some details here. That is, we need to understand what is the origin of this logic. Where is this logic coming from? So this Prim's algorithm logic is coming from cut property of a graph. We need to understand what is a cut and what is a cut property so that you get in-depth idea of what exactly is working in Prim's algorithm. So what is a cut in a graph? A cut in a graph, it is a way of dividing vertices into two disjoint sets. That is, you can see it something like this. One set of vertices will be on one side and the other set of vertices will be on the other side. Then this is called a cut, and there can be many edges which are going through the cut that will connect these two different disconnected parts. So if you get any graph, let us say this is your graph, any graph, you can divide it into cuts. For example, if this is your graph, you can say that these three vertices are part of one cut, and that is one side of the cut, and these two are on the other. So these two edges, one is this and this, these are the edges which are passing through the cut. In such a case, the cut property states that for any cut in the graph, the minimum weight edge which is crossing the cut, that has to be part of the MST. Whenever you have a cut, the minimum weight edge which is crossing the cut should always be a part of the minimum spanning tree. This is the cut property. So if you follow the cut property and now think back to what Prim's algorithm is doing, what it is doing is it is always considering that one part of the cut are those edges, those vertices which are already part of MST, and the other part of the cut are those vertices which are not a part of MST yet. And what are you doing? You are trying to choose whichever is the smallest edge which is crossing this cut. And according to cut property, whichever be the smallest edge which is crossing this cut, that has to be part of the MST. Which means Prim's algorithm in every step is choosing one edge which is surely part of MST. So this is the logic behind Prim's algorithm. Let us get back to what are the steps and let us understand how is Prim's algorithm able to find the MST of a graph. So the first step, as we already said, is to arbitrarily choose the starting vertex. So you can choose starting vertex. This step is simple. You can just pick any random vertex as starting vertex. The next step is to initialize the two sets that you want. One set is MST. MST set is initially empty and you have to keep adding vertices to this MST set, or you can add edges to this MST set whenever you add a new vertex. That is, let us say there is one vertex that you initially had chosen as starting vertex and you have all other vertices on the other side. Let us say you are having this particular edge as the smallest edge which is crossing the cut. Then this edge will be part of MST. So whenever you select one edge as part of MST, you have to add it to this MST set. That is what this MST set is for. Initially, this will be empty. Similarly, you should also have a visited set. What is the use of this visited set? You want to know which are the vertices that are already part of MST. This MST set, it will be having edges. If you want to know which are the vertices that you have already part of MST, for that you should maintain a set of vertices. So this is a visited set. That is, visited vertex means whichever vertex is already considered as part of MST. So using this, you will be able to identify whether a vertex is already part of MST or if it is outside of MST. So this is your second step. Your third step, this is to iteratively go through the remaining steps. So the remaining steps, whatever we are going to say, all these has to be repeated till the algorithm completes. So these steps include, what do you want to do here? Until your MST is completed, you have to repeat these steps. First thing is, you have to find the minimum weighted edge that is connecting this visited set. Visited set basically means whatever is already part of your MST. You want to find the minimum weighted edge that is connecting your visited set to a vertex which is outside of visited set. Outside of visited set means which is not part of MST as of now. So you want to find whichever is the minimum weighted edge that is crossing this cut. that means connecting MST, that is connecting any vertex which is part of MST to a vertex which is outside of MST. So whenever you find that particular edge, what will you do? You have to add this edge to your MST set. Whatever is your MST set, to that MST set, you have to add this particular edge. And after this, you have to add newly connected vertex to the visited set. Why should you do this? Add to visited set. Why should you add this vertex to visited set? Because let us say these are the two sets. This is the set of vertices which are already in MST, and this is the set of vertices which are not in MST. And let us say this particular edge is the smallest weighted edge that is crossing this cut. In this case, you will select this vertex to be part of MST. So what happens? Next time, you should have all these vertices as part of MST, and this vertex should be out of MST. And how do you understand this? How do you say it is not part of MST? For that, you will always verify visited array. This visited set will tell you whether it is already part of MST. So for that purpose, for that identification, you have to update your visited array with the new vertex that you added to MST. You have to keep continuing these steps. That is, identify the minimum weighted edge which is connecting a vertex in MST to a vertex outside MST. Then add that particular edge to MST, and then you have to add that vertex to the visited set. You have to continue this till what point? You have to continue till all the vertices are included in visited set. This also means your MST will be having v-1 edges at this point. So whenever your MST is having v-1 edges, or other way of saying it is all the vertices are part of MST, or your visited set is containing all the V vertices. Whenever this happens, you can stop your algorithm. So this is how Prim's algorithm is going to form the MST. The next question is, how are you going to find this minimum weighted edge which is crossing this cut? That is, we told simply that you have to find the minimum weighted edge which is connecting a vertex that is inside MST to a vertex which is outside MST. But how exactly are you going to identify which is that vertex which is having minimum weight and is connecting a vertex which is inside MST to a vertex outside MST? This is the next question. So let us see how this is done. For clarifying on this, one clarity you need is you need to know what is the input format. You are getting a graph as input. Graph can be inputted in two ways. What are the two ways? One is, if you have a graph, it can either be an adjacency matrix, or you can also provide it as an adjacency list. These are the two ways in which graph can be input. Here we are considering that the input is an adjacency matrix, and accordingly we are going to design how to pick the smallest weighted edge. Okay, so we are considering that the input is adjacency matrix. In the next lecture we'll see what to do when it is adjacency list. Whenever it is adjacency matrix, what you have to do is, one, you have to keep a visited array which will be Boolean. So visited array, whatever we talked here, it is same as that, but it is a Boolean array. It will say whether it is yes or no. Yes means visited, no means not visited, or rather true or false. Next thing is, you should have a distance array. What is this distance array? This will tell you what is the minimum distance of this particular vertex from any vertex which is inside the minimum spanning tree. That is, whatever is the minimum spanning tree you have built till this point, considering all the vertices which are till this point already included in minimum spanning tree, what is the minimum distance of this vertex from any of those vertices? This is what this distance array will say. So initially, the value of distance for all the vertices will be infinity, except for one particular vertex which is the starting vertex. Starting vertex will be arbitrarily chosen by you. So for that starting vertex, you will keep as 0. For all other vertices, distance will be infinity. The next thing is you should have an MST. So this is also what you have to initialize. In this MST, you will be adding each edges one by one as soon as you pick a new edge into MST. The next step is, as we said, you have to repeat these steps. And the first step is to find minimum weighted edge. So minimum weighted edge, which is connecting a vertex inside MST to a vertex outside MST. The question was, how are you going to pick minimum weighted edge? The answer is, in order to pick this, you already have an adjacency matrix with you. In this adjacency matrix, you have to pick the vertex with least value. And how are you going to pick this? First thing is, you have a distance array. In this distance array, you already know what are the distances to each of the vertices. So this distance array is of size V, where V is the number of vertices. What will you do? You will go through this distance array right from the first position, and you're simply going to do a linear search, and you will see which is the vertex which is at lowest distance, that is having smallest value in this distance array. But there is a catch. The catch is you have to specifically pick a vertex which is outside your MST. Many of these vertices, let us say you are already through 3-4 iterations, it may be possible that many of the vertices are already part of MST. How do you identify that? For that identification, you have this visited array. So what will you do? As soon as you are traversing through this distance array, you will see the visited array as well. So when you see the first vertex, you will see in visited array whether it is already visited. If it is already visited, that means it is already part of minimum spanning tree. You will only see those particular vertices which are not visited, that is not part of minimum spanning tree, and among them you will identify whichever vertex is having smallest distance. So this is how you will identify which is the edge which is having smallest weighted, which is the vertex which is having smallest weighted edge from any of the vertex inside minimum spanning tree. So this is how you will identify smallest weighted edge. Once you identify that, what will you do? Let us call this vertex as U. Okay. So U is the vertex that you identified in this step where you want to identify minimum weighted edge. Okay. So what are you doing? You are finding the vertex which is connected by minimum weighted edge from the minimum spanning tree. So once you identify this as U, let us say U is that vertex, what should you do? You have to include this U in MST. So whatever is the edge which is connecting U, you will add that particular edge in MST. And then you have to update this visited array. In this visited array, let us say this is your visited array, corresponding to each of the vertices, it will be written either true or false depending on whether it is already part of MST or if it is not part of MST. So whenever you already picked U as the next vertex, what should you do? You should update the array index corresponding to U as true. This means U is now part of your MST. The next step is you have to update distance values of all adjacent vertices of U. So how do you update distance values of all adjacent vertices? You have an adjacency matrix as input. In that adjacency matrix, you will go to the row corresponding to U, and then you will see for each of the elements. So that will tell you what is the edge weight of UV, where V is the other vertex. So for each of these V's, corresponding to each of these V's, you will see what is the edge weight UV. So in case the edge UV exists, what do you have to do? That means that particular vertex V is a neighbor of U. If it is a neighbor, you have to check whether V is having a lower distance now. Previously, V was having some distance from vertices inside MST. Now that U is also added into this MST list, if there is an edge UV, that can be the new distance of that vertex V from vertices inside MST. So this is a possibility. See, it is still possible that maybe if this is V, distance of this V from this vertex may be smaller than UV. That is possible. We are just seeing whether there is a possibility of updation of this distance. So what should you do? You should check whatever is the existing distance of V. Then you should check what is the weight of edge UV, and if it turns out that weight of edge UV is smaller than whatever is the existing distance V, then you should update distance of V to whatever is the edge weight of edge UV. This is what you have to do. So here, these three steps are now simplified. That is, we explained how to implement these three steps. In order to find the minimum weight, you simply have to go through the complete distance array and keep track of visited array as well in order to identify which vertex is having smallest distance. And then adding to MST is simple. You can simply add into this MST set. And then if you want to see all the neighbors of and visited array also, you have to modify. That is, you have to make sure that this is now visited. And then the important step is you have to identify all the neighboring vertices of U, that is the newly identified vertex, and you have to update the distances of all the neighboring vertices. So you might have thought, why are we going through the complete distance array, and why can't we find another way of finding the one with lowest distance? That is, here you have to traverse through the complete array every time. The reason is, even if you decrease the time here, there is a step where you have to find all the neighbors. If you want to find all the neighbors of any vertex, because your input is an adjacency matrix representation, the only way is to completely go through one row in your adjacency matrix, which means you are anyway going to take order of V time for identifying all the neighbors of this vertex U. Because you will anyway take order of V time here, there is no point in decreasing the time taken in order to identify smallest weighted edge. That is, whichever is the vertex which is connected to MST vertices by smallest weighted edge, there is no point in decreasing the time here. You are free to use order of V time here, because anyway identification of all the neighbors of that vertex will take order of V, because input representation is adjacency matrix representation. So this is why, in order to identify the smallest weighted edge, you are anyway doing a linear search in the distance array. Okay, so you now understood what is being done in Prim's algorithm. Let us quickly go through. You initially select a starting vertex. Then what do? You have an MST set, you have a visited array, you have a distance array, and then you will keep track of one set which is MST set and the other set which is all the set of vertices outside MST. Then you will see whichever is the minimum weighted edge which is connecting a vertex inside MST to a vertex outside MST. You will select that particular edge, you will add it to MST, and then you will add it to visited array and identify all the neighboring vertices of this vertex and update the distances to all those neighboring vertex. Then you have to continue the same story again and again till you complete V-1 edges, or you can say till you make all the V edges as part of MST set. Once it is done, your Prim's algorithm is complete. Let us see what are the time and space complexities here. In case of time complexity, what is the most time consuming operation? One is, in order to find the neighbors, you have to take order of V time every time you have to find a neighbor. And how many times do you have to find neighbors? Whenever you are adding a vertex to the set of MST vertices, you have to find all its neighbors. So every single vertex has to be added to the MST set, which means V times you have to find the neighbors. So finding neighbors takes order of V time, and you have to do this operation V times, which means total time is V into V, which is order of V square. So order of V square time is taken for finding neighbors. Another time consuming operation here is to search for minimum weighted edge. And minimum weighted edge, we already explained that you will be searching in the distance array. The distance array is of size V. So again, this operation will take order of V time. And how many times do you have to do it? You have to do the search V times, which means total will be V into V, V square. So time complexity, it is order of V square. The contribution is from one is searching for minimum weighted edge and the other one is searching for all the neighbors. Both are taking order of V square. So your time complexity is order of V square. What is the space complexity? Coming to space complexity, one is for your distance array. You are taking order of V. For your visited array, again it is order of V. And then for your MST set, this is also order of V because there will be V minus 1 edges in the MST. So total is order of V. So time complexity for Prim's algorithm when it is adjacency matrix input is order of V square. Space complexity is order of V. And in the next lecture, we'll see how can we improve on this time complexity when you have a adjacency list representation instead of adjacency matrix representation.